Okay, so we understand how we're going to place the horseshoe vortices now along this wing. And I've redrawn that here. So here's our wing outline, and then we're going to put these bound portions of the horseshoe vortex along the quarter cord and have these trailing horseshoe vortices coincident from neighboring horseshoe vortices, and those go off to infinity in the direction of u infinity. So at this point, we need to decide how are we going to solve for the strength of each of these horseshoe vortices. So we're going to have n horseshoe vortices, which means that we have n gamma values that we need to solve for. We need to know the strength of each of those horseshoe vortices. So luckily, we have two pieces of information that we're going to use to solve this. One is the vortex lifting law. So from the vortex lifting law, I know that for one of my horseshoe vortices, we'll call it vortex I, the force, so the force that is produced and the direction of the force of that vortex is equal to rho times gamma I times the local velocity cross Li. Okay, so let's define some things here. Here we've got our some horseshoe vortex I, and we're going to call this L sub I. This is the vector connecting one corner to the other, and then we're going to have some strength gamma gamma I, and so from the vortex lifting law, we know that the force that is produced by that horseshoe vortex, by that bound portion, is equal to the density times the strength times V cross L. Okay, V is the local velocity. So let's actually look at this from the side for just a minute. So if we're looking down the length of that, we've got some strength, and then if we have some incoming velocity, V sub I, then the force that comes off of this vortex will be perpendicular to that. That's the force. It's perpendicular to V and it's perpendicular to L. Okay, so that's where we get this as V cross L. That gives us the direction of that force, and then the magnitude depends on the magnitude of V, the magnitude of L, and the magnitude of gamma, and obviously density as well. Okay, so that's the vortex lifting law. So this is one piece of information that we have. We know that if we knew the strength of that vortex gamma, we could figure out how much force was coming off of that. Well, because we're talking about an inviscid solution here, that force from the Kutta-Joukowski law is actually equivalent to the lift, right? Lift always operates perpendicular to our incoming velocity, our local velocity. And so the second piece of information we have is actually about that lift. If we were to slice up this wing and look at that horseshoe vortex, it would be representing basically the aerodynamics of a cross-sectional or a section of this wing that has some airfoil geometry. And from that airfoil geometry, we know a lift coefficient, and again, this is section I. We have a two-dimensional lift coefficient that is a function of the angle of attack, and we can also say that it's a function of flap deflection. Okay, so it's a function of angle of attack of that airfoil. So this is our local V, and so we'd have some angle of attack I, and then if we wanted, we could include some flap deflection back here, which would be delta I. Okay, so from airfoil theory, we know what the lift coefficient would be as a function of alpha and delta. And so these are two bits of information that we have, and actually all we're going to do to solve this problem is we're going to equate these two. We're going to say that those two have to be equal. And actually, this is the exact same approach that Prandtl took in developing the original or the classical lifting line theory. So we're going to follow that same idea here. So let's just write that out. Actually, we can't equate a vector to a scalar, right? So this force up here is a vector, and this is a scalar. We can't directly equate those, but actually the force has a magnitude, and that magnitude, let's just write it out here. So the magnitude of that force has got to be equal to, now this is a dimensional force, and so let's put the lift coefficient in dimensional form. So that's going to be 1/2 rho times v. Now, let me just put v infinity here for just a second. I'm going to come back to that in a second. 1/2 rho v infinity squared times the lift coefficient I, which is a function of alpha I and delta I. Okay. And we need to multiply this now by a spanwise or by an area, because actually we have a full area. We have a spanwise length here represented by this DL, up here. So we have some spanwise length, and so with our chord and our span, now we've got some complete area there. So we'll call that S sub I, okay? So that's the planform area. Now let's come back to this V infinity. So actually, I'm following the algorithm published by Phillips and Snyder, and I failed to mention that earlier. This is by Phillips and Snyder, published in the Journal of Aircraft in the year 2000. You can go look that up. I'll leave a link at the bottom of the video as well. And they use V infinity here. Now, I actually think it's more correct to use the local velocity V sub I, because that's the, you look at this drawing over here, our local velocity is V sub I, which is, we're going to find is different than V infinity. Okay, so we're using V sub I here in the vortex lifting law, and I think to redimensionalize this lift coefficient, we should be using the local velocity V sub I, or the magnitude of that, squared. Okay, now they use V infinity squared, and I'll just make a note here. This could be or V sub I, actually the magnitude squared. Either way, you'll get very similar results. But anyway, that's just something to note. Okay, so one other thing that I want to note is that, so this is the same equation, basically, that Prandtl solved in his classical version, but in his classical version, he assumed that lift was a linear function of alpha, okay, or of angle of attack. And so he assumed that this was just a lift slope times an angle of attack. And we also could account for a flap deflection there as well. But the point I want to make here is that in this algorithm, we can actually just say that lift coefficient is a function of alpha and delta I. And this is a little bit more powerful because this allows us to take into account nonlinearities in lift as a function of angle of attack or delta, and actually even use experimental data and begin to capture some of the effects of stall, where the traditional classical form of lifting line theory was unable to do that because it assumed that it was just that lift is a linear function of alpha. So if we had, for example, some experimental data for lift as a function of angle of attack, we could actually use that in this equation. You're going to see that the way we write the final form of this, we can actually just use that in there if we like, and be either interpolating in that data, or we can fit some polynomial to that, or still we could assume that it's just a perfect linear relation. Anyway, any of these will work in this algorithm, which makes it a little bit more powerful. Not only that can account for sweep and dihedral, but can also account for these nonlinear effects or aerodynamic relationships. Okay, so we've got our fundamental equation here. This is this is really the crux of this algorithm here, is that we're going to equate these two different versions. And actually, this closes our system of equations. What we want to do is develop a system of equations that allows us to solve for n unknown gamma values, right? And it turns out that this system of equations does that for us. So we have all the information that we need. So let's dive into this just a little bit more, though. One thing we haven't defined here is v sub I. So our induced velocity at this horseshoe vortex. So for example, from the vortex lifting law, we need to know what our local velocity is. And depending on how you treat this, we might need to know what the local velocity is. Certainly, to get the local angle of attack, we also need to know the local velocity. We'll talk about that in just a moment. So anyway, we need to know what the induced velocity is at one of these horseshoe vortices. And actually, it changes along the length of this because that induced velocity depends on the influence of all the other horseshoe vortices as well as the free stream velocity on that. So what we need to do is we're going to choose a control point along there, and we'll talk about how we place those control points here a little bit later. But we're going to just choose a point and look at the induced velocity at that point, and we're going to assume that that the induced velocity is constant over this horseshoe vortex, or along this length here, this bound vortex length. And that's not really true, but as we refine the grid, it will grid resolve and give us a good solution. So okay, so the velocity induced at point I, or at horseshoe vortex I, is equal to, or the total velocity, I should say, is equal to the free stream velocity, v infinity, plus that induced by all of the horseshoe vortices. So I'm going to use J to loop over all of the horseshoe vortices and say that, and actually we can scroll back up here to the influence of, now this equation here shows us the influence of a single horseshoe vortex on some point in space. And so actually we're just going to use this exact same equation, and this portion in the parentheses I'm not going to rewrite. You can come back up here and copy it down. So let's see, it's just going to be the summation of all of those horseshoe vortices. So that would be gamma j over 4 pi times the stuff in parentheses, and we're going to call the stuff in parentheses v j I. So this is the influence. This is an influence of horseshoe vortex j on point I. Okay, and so again, you can come back up here. This stuff in the brackets is what I'm calling v j I. Okay, so that's the influence of horseshoe vortex j on point I, and for each of those we would have to solve for R1 and R2, right? So we'd have to figure out, we know where our point is, we know where our horseshoe vortex j is, we have to solve for R1 and R2 and plug them into this equation. Now there's one caveat here, and that is that when j equals I, we're looking at the influence of a horseshoe vortex on its own control point. And in that case, we actually want to neglect the bound portion, and that's this portion right here of this equation. That's the influence of that bound portion. These other two are the two trailing vortices, right? So we've got these two trailing vortices. We want to still include those, but we don't want to include the bound portion. And that's because the bound portion actually doesn't induce a velocity on a point that is coincident. Any of these, any segment doesn't induce a velocity at a point that is coincident with that segment. And you can see that actually, again, if we turn this sideways and we draw this this vortex going in and out of the page, and then if we were to plot the influence as a function of radius, let's just say a radius as we move away from that point, we'd see that the influence is, I believe it's a 1 over r squared influence that goes to infinity as you approach 0 from either side. But at 0, actually, it doesn't induce a velocity. Okay. Now, if you leave this term in and try to compute the influence of a segment on its own, on a control point that lies on that segment, you will get probably a non-zero value, and that's because you're going to have some numerical round off things just due to computer precision and things like that. And so it's best just to neglect this. So anytime I equals j, you just neglect this term, okay? And we're not violating any laws here. We're just saying this really should be 0, and so we're going to just force it to be 0 by neglecting it rather than playing with any numerical round off in there. Okay, so this is, back to our equation here, this is the velocity at point I. It's equal to v infinity plus the summation of all of the influences of the other of all of the vortices across the entire system of lifting surfaces. Okay, now one last thing we want to define here is our angle of attack. So this is our v, this is our induced velocity, and then we also want to know what our angle of attack is. And that's, right in here, we need to know what the angle of attack is to compute our local lift coefficient. Well, the angle of attack is equal to tangent minus 1 of my local velocity vi dotted with my unit normal I divided by vi, my local velocity dotted with a unit axial. Okay, now the unit normal and unit axial, we can draw those on this section over here. We're going to have some axial direction, so we'll call this the axial, unit axial, and then we're going to also have a unit normal. That's some direction, okay? And these will be different for each, or can be different for each wing section, depending on the local dihedral and twist. And anyway, you can, the different geometric properties of that wing, the normal and axial unit vectors will change or depend on that. So anyway, this gives us now the angle of attack as a function. Notice again, this is a function of v sub I, which depends on, from this equation here, depends on all of the vortex strengths. Okay, so we can now take this alpha I definition and our v sub I definition, and we can plug this in to our f sub I definition. See, that has a v sub I in it, and then plug that here into this equation, and then rewrite this. I'm just going to rearrange this slightly. So what we get is the magnitude of f, and instead of for this guy here, I'm actually going to plug in what we have up here for this equation. So the magnitude of rho times gamma I times vi. Now instead of vi, I'm going to plug in this equation here, which is v infinity plus the summation from j equals 1 to n of gamma sub j over 4 pi v ji. That's that influence matrix again, or influence vector. And then I'm going to, then we've got this cross L sub I, and we're taking then we close our magnitude here. That's the magnitude of the force. And then that's equal to, and I'm going to move this stuff over to the left-hand side. So I'm going to say minus 1/2 rho. Again, I'm going to use v infinity squared, but really that could be the magnitude of v sub I squared times the local lift coefficient, CLI, as a function of alpha I and delta I, where alpha I again is given by this equation over here, and that equals 0. Okay, so this is our equation now that can actually be written for every horseshoe vortex. So we have an equation that must be satisfied at a single horseshoe vortex and actually must be true at every horseshoe vortex. And so what we get here is a system of n equations to solve for our n unknown values of gamma. Okay, so I'm just going to kind of block this out here. So we can write this as a system of equations where we're solving for gamma sub I, or our array of gammas, and then we can So our system of equations can be written something like this, where now the challenge here is that this is actually a nonlinear system, okay? So we can see that. That's pretty obvious because v sub I, we can see we need v sub I in order to compute our alpha, and that v sub I depends, remember, on the gamma j values. Well, we don't know what gamma j is. We're trying to solve for that. And so this is going to be an iterative process where we're going to solve for a set of gamma values. Then we're going to plug those back in to v sub I. We're going to recompute alpha I, plug that in here, and then solve for a new set of gamma values. And anyway, we're going to have to iterate through this. There's a few different ways to do that. The way that Phillips and Snyder suggest is by using a Newton's method, which actually converges quite rapidly. So I'm just going to put that here, and you can look up their method. They actually come up with an analytic gradient of this equation, which is really helpful, speeds up the Newton's method, so you don't have to do finite differencing, or but you can work through an analytic gradient of this main equation to compute your residual, and anyway, it speeds up the solution process quite a bit. So they suggested Newton's method. Now there are a lot of ways you can solve this. Any method of solving a nonlinear system of equations should work, and from my experience, this is a fairly well-behaved system and solves rather rapidly for points that are not flirting with stall. So as soon as you get up here near your stall region, then this system of equations is really difficult to solve, and you start to get some kind of weird behavior as you move over here. And so that's why, I say that it's really good for predicting kind of stall onset. You can kind of capture this nonlinear region here as you approach stall, but then once you pass stall, this system of equations really isn't very good, or this method really isn't very good for predicting what's going to happen post stall. Now, that could be changed. Maybe that's an area of research that somebody could undertake, trying to get this to work at higher angles of attack to better capture stall characteristics. Now, one more thing I want to point out here is that Phillips and Snyder actually write their general equation in a non-dimensional form. Okay, I've left this all in dimensional form here. I think it's a little bit more straightforward to think about, but they go through and non-dimensionalize the system of equations, which, there's nothing wrong with that. It's just another way of looking at it, another way of solving it. No, it's not necessarily better one way or the other. I guess the nice thing about the non-dimensional form is that your free stream velocity doesn't really matter once you divide it out, and if you're only interested in like lift and drag coefficients across the wing, then you can get that kind of non-dimensional information out by just non-dimensionalizing this system of equations. And then anyway, there are some benefits to working in the non-dimensional world, but then there are also benefits to working in the dimensional world that you can't capture as well in the non-dimensional world. So anyway, there's pros and cons to both ways. I've just left it here in dimensional form.